Suppose a particle is launched with a speed u at an angle theta to the horizontal. So the initial velocity vector is u. Let's put the origin of a coordinate system where the particle is launched. Now the mass of the particle is actually irrelevant because the acceleration of the particle is constant for any mass. We know from the previous video that ux, the x component of vector u, is got by multiplying the magnitude of vector u, which is u without the arrow, times the cos of this angle. And the y component, uy, is got by multiplying u by the sine of theta. If you like, we can use I and j basis vectors. Vector I is a unit vector pointing in the positive x direction, and vector j is a unit vector pointing in the positive y direction. By unit vector, I mean a vector of length 1. We could consider the position vector of the particle. Suppose the particle gets to here. Well, it will get to here, but let's suppose it's at this position. This vector here is the position vector. We can call it S. S is made up of two components. An x component, which we call Sx, S sub x, and a y component, which we call S sub y. So to get vector S, we add vector S sub x times unit vector I onto S sub y times unit vector j by the triangle law. Now, we saw in the previous video that S sub x is ux times t plus a half ax times t squared. We covered this formula in linear motion with constant acceleration, and that's what we have. We have constant acceleration in the x direction, but the ax is actually 0. So S sub x equals ux times t. We saw that ax is 0 in the last video because the force on the particle in the x direction is 0. So if there's no force in a particular direction, it means there is no acceleration in that direction. So the x component of the particle's acceleration is 0. So this gives us the x position of the particle at any time t. We don't have to write s sub x, we could just write x. And of course we know what ux is. Ux is u cos theta. So we have that x, I just write x here, equals u cos theta times t. So we can find the x position at any time t. We just plug in for t. T is the variable. U cos theta is fixed. It's the initial, it comes from the initial velocity of the particle. We can also consider s sub y. That's the y value of the particle's position, the y coordinate of the particle. The particle has coordinates xy. We don't have to write s sub x, s sub y. We can just write y. It's just that the letter s is traditionally used for the position of a particle that's moving uniformly in a straight line. Uniformly means uniform acceleration. So ay is constant acceleration. So we're talking about the y component of the position of this particle. The y component of the acceleration is constant. Ay is minus 9.81. We saw that in the last video. So we just plug in here for uy and ay. Uy is u sine theta, so I'll just write y here. Y equals u sine theta times t. A half of minus 9.81 is roughly minus 4.9. We want the equation of the trajectory of the particle. So we need to solve between these two equations in order to eliminate t. So we have the parametric form of the equation of this trajectory. We have x in terms of a parameter t and y in terms of a parameter t. So we need to eliminate t between these equations. Well, the easiest way to do that is to take this equation here and make t the subject of it. So we just divide across by u cos theta. And then we substitute this in for t in the second equation. The u's cancel here. Sine theta over cos theta is tan theta. So we have tan theta times x, and here we have minus 4.9 times x squared over u squared cos squared theta. So this is the equation of the trajectory. This is the Cartesian equation of the trajectory. You see that tan theta is just a constant, and so is this here. This is a constant. This never changes, because u is the initial speed, theta is the launch angle. So they're fixed. Now, notice that this is a quadratic function. Quadratic function of x. See, we have x squared. The graph of a quadratic function is a shape called a parabola. Notice that the coefficient of x squared is negative. See this minus sign here. Everything else here is positive. 4.9 is positive. U squared is positive. Cos squared theta is positive. We have something squared here. So we find that the x squared term is negative. So you might know that if the x squared term is negative, we have an inverted U shape, an upside down U shape. Let's get the equation of the trajectory of a particle launched with a speed of 44 meters per second at an angle of 47 degrees to the horizontal. So here's the equation of a trajectory. In this example, theta is 47 degrees. So we get that y equals the tan of 47 degrees times x minus 4.9 over the initial speed u, which is 44, squared times the cos of 47 squared. So this is the equation of this particular trajectory. Working out the coefficients, we get the equation of the trajectory. Now I've written out the coefficients to, well, I've written this one out to 5 decimal places. I've actually written this one here out to 7 decimal places. The reason I did this is because I want to look at the range of the trajectory. That's this distance here. Now in the last video I explained how to calculate the range, but this time we're going to use the equation of the trajectory to get the range. Basically we set y equal to 0, because when the particle is here, the y value is 0. Of course, when the particle is just launched, the y value is also 0. So we put 0 equal to this, we factorize x out, and we put each factor in turn equal to 0. Of course, if we put this equal to 0, we get the trivial solution x equals 0. That's when the particle is launched. And if we put this equal to 0, we get x equals 1.07237 divided by 0.00544416. To the nearest integer, that is 197, which closely agrees with this value here. This value here is 196.9. I will probably get an even better estimate if I was to take more decimal places in the coefficients. Let's look at the time of flight. Well, we can use this formula here for the x position of the particle. Ax is 0 because there are no forces in the horizontal direction, so we can forget about that term. So the x position is ux times t. So what is the x position when the particle reaches here? Well, it's 197 approximately, or 196.9. We'll use 197 equals the x component of the initial velocity, which is 44 cos 47 times t. So t here will be the time of flight. So we just divide 197 by 44 cos 47. If you do that, you will get to one decimal place 6.6 seconds. So it does check out. So we're doing this in a slightly different way than in the previous video because we know the range of the function. We know from the last video that the time it takes for the particle to reach its maximum height, which is here, is half the time. Is half the time of flight. It's half of 6.6. So that's about 3.3 seconds. So it takes 3.3 seconds for the particle to reach this point, the highest point. To get the maximum height, we apply this formula for linear motion with constant acceleration in the y direction. So the y component of the initial velocity is 44 sine 47. And t is the time taken for the particle to reach its maximum height. T is 3.3. Now we've a half times the acceleration, a half times the y component of the acceleration. Well, the y component of the acceleration is minus 9.8. The acceleration is in the negative direction. So this direction is positive. Since the acceleration vector is pointing down the way, its direction is given by the minus sign. So we minus a half of 9.81, that's minus 4.9, times 3.3 squared. So we get 52.83 meters for the maximum height. Now we could have found the maximum height a different way, because we have the equation of the trajectory. Normally we don't have this equation. Let's do it a different way. We know that the equation is a quadratic function, which means that the shape of the trajectory is a parabola, an inverted parabola actually, because the x squared term is negative. A parabola is a symmetric shape, so we can use that symmetry to find the coordinates of this point here. The x coordinate is half the range, it's half of 197. That's 98.5. Since this point must satisfy the equation of the trajectory, we just plug 98.5 in for x. You can check that we do indeed get 52.83 meters.